Okay, thank you, Chairman. I'm here, so you should not sing. And I would like, by apologizing, I did not prepare a talk for physicists. I prepared a talk for general audience. And the idea is if we can understand how the concept of atom came across and how it got involved and penetrate in other fields like biology and many others. Today we saw in the morning that there was a statement that we cannot explain turbulence using the equations that govern atoms, and I think it's the opposite. You know, if we understand well how atoms behave, we can explain a lot of things, including turbulence. I am an atomic physicist. I work with cold atoms, and in fact, I work with quantum turbulence, and this is what we are trying to do in my lab. Okay, so I will, part of my presentation, Professor Hensch already presented, so I can go very quickly and spend more time in the applications. And my idea here is to show you the understanding of science, the understanding of the concept of atom, and how is that solving problems of society. And, you know, there are many examples I could choose, and I chose the cancer and microbiological control because I know in the academy there are many people in biology, and I can see how they feel just looking to those constants, and maybe I can explain to them why we are so interested in understanding the atom, in understanding the concept of how is that formed in the universe, because that is actually very relevant for many of the things we do. Okay, so you know, the questions that we are always looking to answers is what is everything in the world made of, how things come to be what they are, and how we see things the way they look to us. And this is what I'm going to try to show to you. And one of the biggest success in evolution is when man was able to connect the micro world, the small scale, very tiny scale, to the world that we see. And I think this is what every physicist is looking all the time. You know, doesn't matter how small is the scale, can be the elementary particles. You know, for us is very important, for atomic physicists, it's very important how we start with the concept of atom and explain most of the things we see around us. And I think this is an important example of success in the evolution of concepts in science. Of course, we'll be speaking about the atom. Atom has a timeline of understanding. We already hear today many things about the ancient time, so I'm not going to go to that. And then this concept came passing to many important people until we all realized that, oh, it makes sense to speak about atom. And then we had to speak about what's the atom made of. And then we had to speak about, oh, but how is those constituents arranged? And I think this was the origin of this modern science, which is the quantum mechanics that we all work and has big implication in all the fields we touch. Okay, so, and of course, atoms, we don't see atoms. I mean, we see what atoms tell us when interact with light, when emits light somehow. So we see the energy that comes from this interaction. And mostly atoms and light is what determine most of the applications of modern technology. I don't think any technology that doesn't touch atoms and light. And maybe that's why light is so important to the next year, to remind that we only see light, right? And we try to infer about everything through the light we see. Okay, so before I think we already hear many things today, and you know, people had all this idea that things should go to very tiny, and all the matter should be composed of small object that they call atom. Maybe the idea was not completely correct at that time, but you know, they know that it doesn't make sense to have so many so large variety of things in the universe if there was not fundamental little pieces to make them, right? And then the things evolve. We had what I call the chemical atom. I think chemistry had a lot of influence in what physics is today, because they were the first to come with ideas, you know, like the law of proportions and everything, that somehow induce us to go and look for the atom, you know, really more evidences of the atom. And the laws of transformation, you know, Lavoisier with their laws already indicate that something, you know, we had to have small parts moving around to transform pictures, and those are the atoms as we know today. And the concept of mole. I think the chemistry came with a concept that let us understand what was the dimension we were talking about. And the first big success of the concept of atoms, I think, came with explanation, because in physics we have some hypotheses, and we see how that can be reality by explaining some important features. And the gas law, you know, trying to understand how a gas works, because gas, everybody plays with gas. So if we understand and we can explain that based on atom, that could be a good evidence that, okay, those tiny objects really exist. And gas is the closest thing we have around us that are individual atoms. Solid matter are composed, you know, and gas normally is the closest thing we have of individual atoms. Maybe if we have to start explaining something, imagine the idea of atoms, gas will be the good one. And in fact, the history told us that the first thing they explain is how was the behavior of gas. If we imagine then by composed of tiny little objects of mass moving around. And as a bonus of that, we got the interpretation of temperature, which is also, you know, very important. Before that, we all knew the concept of hot and cold, but we didn't know how to connect that with the microscopic world. And the atomistic idea of gas and the motion and the fact that a balloon keeps inflated because of the force that those tiny objects can provoke on the walls was essential for us to believe that atoms exist. So atomistic, you know, the laws of gas was a very important point, and maybe it was one of the first really evidence that we could go on in that direction and try to search for the atoms. And then the next question is, what is the size? And again, the chemistry helps a lot because they knew the proportion laws, they knew the concept of mole, and if they could find how many atoms are there in a mole, we could somehow know the size. And actually that happens, and there was many methods that was devised to measure, you know, the mole, the number, the molecular number, and the number of atoms that compose a mole, and that gives us the dimension. So once we know the dimension, we know what object we are looking for. And then the whole thing starts. And there was many, many things in between. The idea of the atom and the size and the start of experiments, many experiments on discharging gases, because as I told you, gas is the closest thing we have that we can consider as individual atoms adding their properties to make the macroscopic observation. And then comes the electron. You know, everybody knew electricity is another old concept, but was Thomson that really came and measured and find out that, oh, we have this tiny little object which is responsible for all electricity, and it must be inside the atom. And then, you know, if we move, and then they measure the charge of the, because Thomson measured the ratio between charge and mass. Those are important things, you know. I think the nature we see is all consequence of charge exchange and chemical bonds, which is a kind of charging share between atoms and everything. So those discoveries really put atomistic or the atomic concept of nature on the scenario. Of course, after they discovered this, they had to know how the constituents of an atom are arranged. And Professor Hensch already showed to you the experiment of Rutherford. And Rutherford showed to us that all the mass and the positive charge is concentrated in the center, what we call the nuclei of the atom, and the electrons must be around. So all the other models could not explain the observations. So then we start, with this idea of what we call the orbital atom, which is electron that should be around the nuclei. And then there are the problems. An electron cannot sustain itself around the nuclei. It will drop inside, emitting energy all the time, and that provides us some evidence that something else should be there. And Bohr, last year we celebrated the centennial of Bohr atom, which I think was fundamental, and also Ted Hensch already showed the importance of this. Even though Bohr had, was close to what should be, he said that something very different should be there. And he thought out of the box and proposed something that nobody could believe, that is, maybe we have to violate everything we know to explain how an electron can stay in an atom. And that was the beginning of quantum mechanics. The difference of Bohr atoms that says that electron can stay not in any orbit, but in a few orbits, was very important. But then they evolve a little more, and that's the tiny little picture there that you cannot see, but I have a Schrödinger, I have Einstein, and I have many other guys there that said, look, we have to look at the atoms not like an electron orbiting, but we have to give another interpretation. Electron is like a cloud of charge around the nuclei. And because it's not any distribution that's possible, and this is the main concept of quantum matter, is that not everything is possible. Only a few things can match the boundary conditions. So if electron is bounded by these nuclei, only a few distribution of charge is allowed, and that's the origin of those orbitals that biologists and chemists use a lot. And this gives us another concept, that the discrete possibilities of energy arrangement and charge distribution on the nuclei. And then we had to explain this. We have to come with equations. As was said today, equations is a nice way to translate observations in the paper, in a way of thinking. And the same way that mechanics is fully governed by Newton's law, we had to come with some equations that explain the behavior of the electron in the atom, and that is the quantum mechanics, the Schrödinger equation, which you don't have to worry about. The only thing is that this equation predicts the things we observe, predicts that electron cannot be in any configuration. It has to be in a few configuration that we call amplitude of the wave function. And that gives to matter all the properties we observe. Structure cannot be any. When two atoms approach each other, they have to form a special structure. And that gives the variety of molecules that make life, right, as we know. Okay, so then many people contribute to many things. And here we come at the end with the conception, how is, the microscopic world composed of those tiny objects, which are the atoms, moving around if they are not in zero temperature. And in fact, this motion that you see, which is related to the temperature that the molecule is present, is essential for keep going with the reaction. It's very nice to see the evolution of biochemistry, but atoms meet each other most part of the time by random walk, and temperature in this case is very, very important. That's why reactions always freeze when we put the temperature down. They stop to take place. So this is the vision of the molecule now, and they make a big difference for many things, And I think these things that I took from the web, atoms for the next generation. Maybe this is already like 20 years old, but it's truth. I mean, almost no technological development can go on if we don't take serious the idea of the atom and better understanding of this atom. So just understanding that everything is made of atom doesn't explain everything we see, right? We have to understand why these beautiful colors come from, how they are, what they are, how things change. And to do that, we have to start by looking light. There is no other way of really interacting well with atoms. Well, there are many ways, but light, because atoms is made of charges, and light has this electromagnetic nature, which is also electrical in some sense. And this is Maxwell that 150 years ago, next year, predicted that light has everything to do with electricity, made a big difference in how we see the world. And in fact, this is one of the reasons we are celebrating the International Year of Light. It's the anniversary of the understanding of light as an electromagnetic phenomenon. So if we understand that light is made of electricity, then the interaction with the atoms is fully understood. Because you see, electricity likes charge. I made this cartoon because I know that's an easy way of understanding. You see, you have this charge distribution, which is atoms and molecules, doesn't matter. When light comes, light is electrical field, can interact with those charges and modify their structure. We call this transition in atomic physics, but we call also excitation. And that's maybe the most important way that light can transfer energy to matter. In fact, if it wasn't this, I don't think life will exist in the Earth, because the only energy that can organize the atoms to make life is the energy that comes from the sun, which is pure electromagnetic wave interacting with atoms here in the Earth. Okay, and when the light interacts with the atoms by the charge, right, and there is also some magnetic interaction, which to simplify, I'm not including, many things can happen. First, this distribution of charge can change, and this we call electronic excitation. But it also can rotate or vibrate. In fact, that's why the microwave works, and we use every day to heat up water and food. So basically, this is another cartoon, because the electronic distribution in the atoms can exist only in a few configurations. That's predicted by the quantum mechanics. When we put light, it's easy to see. If you have an electron distribute like in a sphere, an electrical field will somehow drag this and make it appear like the other distribution. And this is what we call the S to P transition that Professor Ted Hensch is famous by studying some of these transitions in a hydrogen atom. And then, the system likes to come back. The same way that absorbs light to change the configuration, it gives light back when changing the configuration. Okay. So, because of this process, many things can happen. Like, I give light to the atoms, atoms give light back, and this is called fluorescence. Or maybe I give light to the atom, change this charge distribution, transfer the energy to other molecule. This happens in your body all the time. I don't know how many trillion times per second. There is collision quenching, which is modification of structure and energy dissociation, internal rearrangement, and chemical reaction because of those excitations. So all this happens, and we understand quite well that happens. Those are a few of the phenomena that takes place. And using those phenomena, we have been able to do many things, including a better understanding of the atom. And since we understand so well now, or at least we believe we do, the interaction of light with the atoms, we can control their motion. And controlling their motion, we can really almost stop this entity called atom in space and do a better understanding. But surprisingly, when we stop them in space, as I told you, their motion is related to temperature. If we remove motion, means that we are going to another stream of temperature, which is close to absolute zero of temperature. And a lot of people are studying this and discovering a whole new universe of a phenomenon that takes place. William Phillips is also a member of this academy and got Nobel Prize by advancing techniques to cool the atoms. And Professor Hensch also used atoms to better clocks and to understand better many things, or to simulate other things of matter. So understanding, now we are in a situation that we understood the atom, and then we evolved to manipulate the atom. So using the light that interacts, and light is like energy, but is also momentum, following the ideas of relativity, we can also control motion. We can make force on the atom and produce matter very close to the absolute zero, where we do study many things. Okay, so this is one stream. And now today, you know, people are already speaking about quantum computer. Atoms are so rich because we have those specific configuration of charge distribution. We can accumulate energy in that structure. And if we can accumulate information in that structure, means we can do calculus. You know, we can do binary system. We can make what we call entanglement, which is mix two atoms interacting each other, and make sure that we know, use that amount of energy accumulated there as a storage of information. And this is the basis of quantum computation. We can also simulate things that nature doesn't want to show us very easily, like a solid. You know, a solid is a so complicated system. It's too many atoms together, interacting each other, interact with the neighbors and the near next neighbors, and it's complicated. So people are able now to make an equivalent of solids, putting atoms arranged in space, using light as the binding energy of those atoms. This is another evolution, because we are finally understanding things that we could not understand before. But nothing so important than life, right? And the concept of atoms took a long time for biologists to adopt the molecular biology name, because now they know that the basis of everything has to be there. And they are changing their concept. We know the modern biologists, they have to be molecular physicists together with molecular chemists to understand what's going on. So the concept that we have what we see in the macroscopic world, which is the body, has to be related to what we do not see, which are the molecules. And this changed completely the way we see the life and the way we can control and help people. And, you know, we expended more than a century trying to understand well how light can interact with the atoms. How can we excite? How can we make them interact or not? Why not use this inside a cell? So now I'm going to tell you what can we do for a little bit of sample of atomic and molecular physics inside the cell. You know, we are not transparent. And the reason that we are not transparent to all colors is because somehow light has to excite those charges the way I explained to you and convert energy in something. If nothing, you ionize. If you send so much energy to the atom, you shake the cloud of electrons so much that you ionize. This is a very simple vision of ionization radiation. And if you ionize, you can change the structure, because the structure of the biomolecules is a very detailed equilibrium between this charge distribution. When you remove a little bit, you know, structure can change. And if somehow that structure determines the course of life, function of the cell, then you made a mutation. You're going to change that. But a lot of times, those excitations can actually change many things, or maybe even identify things. We know today that you cannot do microscopy without putting special molecules inside the cell to attach to different sites of the cell, so we can identify those sites through interaction of light and molecule. But we can do even more than that. So let's try to do some examples of how can we export atomic physics to the internal cell. You know, atoms are there, and depending on how the cell is doing, different atoms are there in different structures, in different distribution. So we can do diagnostic. Or we may modify that. And sometimes we want to kill the cell, like a cancer cell. If we can modify that such that cell die, oh, that's a good therapy. So understanding how light interact with atoms themselves, we are able today to do many things. Today if you go to an ophthalmologist that does not have a laser to go and do things in your eyes, he's not doing well. Or maybe in a cardiac surgeon, because today people can do holes inside the muscle of the heart to simulate vessels and avoid you to die in a heart attack. Or maybe the tissue regeneration with light. This is already in practice. Just by stimulating the right molecules that are in the tissue, we can make them react fast. We can stimulate mitosis. We can stimulate vessel formation. And we can regenerate wounds like this one that sometimes take years to be regenerated. Well, this is just a plot showing this is the cell division, label index people measure, and in the presence of light, exciting the correct biomolecules, we can multiply the mitosis by a factor of 3. And in fact, in some applications of medical applications, they are using that as an important tool to help in the recovering of things. But there are some challenges, and there are 2 challenges that I consider very important. One is cancer. Everything we do is still not enough. We have it at the same time that we understand we have to come with different ways of killing. And microorganism control. We don't know what's going to be because microorganisms, they already decided to be resistant to many drugs. And then we have 2 challenges to face here. And it's possible to think that atomic and molecular physics can help that a lot. Of course, that's the only way of doing because everything is molecular there. We got to find ways of doing that. And then I'm going to just show you some example using cancer as the target. But before doing that, let me explain a few details that I left behind. Let's take the oxygen molecule. Everybody agrees that this, after water, this is the most important molecule we have. And, it's 2 oxygen atoms together. Quantum mechanics for each atom determine how the charge distribution has to be around each atom. And then they combine, and quantum mechanics also tell us how will be the combination. And I did not say anything about this spin, which is a property of the electron that I left behind in my timeline. And this was very important discovery. It's a property of the electron that somehow makes quantum mechanics more exciting. Electron can have spin, it has the spin, and it has a spin half, so it means has a kind of angular momentum. And because of the spin of the electron, Heisenberg, Pauli put some principles that the way electron can combine depends on that spin. It turns out then that the oxygen molecule that's very useful for us because they combine more than one electron, depending on their spin, which is this tiny little arrow that we represent in those diagrams. I'm sorry, we cannot see very well from here. The molecule changes completely the behavior. So oxygen that's fundamental for life, and mitochondria, cycle, and everything, can be deadly for the cell if we change the spin of the electron. So atomic physics knew that much before we learned in biology. But when we change the spin of the electron that makes the bond in the oxygen molecule, we call what we call the singlet oxygen, which is a free radical. And this free radical is too many energy in there that needs to be released, and when find the double bonds or any other molecules, just released by oxidation. If we oxidize molecules, we destroy them, like the fire, right? So, if it is possible to go and do this atomic change or molecular change inside the cell, we can produce an enemy for the cell. Sometimes that's important because we want to kill that cell or a specific microorganism. And this is what's being done today. I'm sorry, this cartoon is in Portuguese because it was published in a Brazilian journal. Imagine I have a molecule there. It turns to be a porphyrin or a chlorine. Those molecules absorb light and produce another charge distribution. Then when encounters an oxygen molecule, transfer this energy to the oxygen molecule and produce the singlet oxygen that's inside. So we had the triplet oxygen, which is the good oxygen. But if we transfer energy to that, it became a free radical. And this free radical can oxidize the cell. And by doing this, we can kill cancer, for instance. So suppose I put this molecule and find a way of them to find the cancer cell. I just needed to illuminate a tumor, and they die immediately, seconds after I illuminate, because biological tissue does not resist to strong oxidation. And a tumor like this, an exophytic tumor, comes out. This is the leg of a patient. Can be killed by oxidation. And this technique is being applied to many things. Intraoral, this is example. I'm going to scan to a few examples of cancers that could not be cured without this new molecular physics or photophysics inside the cells. So those are cancers that were removed by 20 minutes illumination. The idea is very simple. You put a substance and you illuminate, excite the molecules inside the tumor, and remove the tumor. So those are examples. This is oral cavity cancer, a squamous cell carcinoma, and many others, as you can see. And this became an important technique all around the world. This is a tumor of the larynx. Normally, physicians have a hard time in removing those tumors. But with these new techniques that rely on doing atomic reaction, molecular reaction, inside the cells are making a big difference. Intestine tumors, recurrence, breast cancer, recurrence, esophagus, and skin. I'm engaged in this program because in Brazil, we have 400 new cases of skin cancer every year, and 47,000 melanoma, 400 no melanoma skin case. And this is a big problem for Latin America and all the world. It's a health problem, it's a social problem, because it's been impossible to offer treatment for all that people. It's an economic problem, and it's logistic. Normally, to treat cancer, you have to transport patient. With a country like Brazil, is impossible. We are too big. So this technique is helping, and if it's well developed, we can really make a big change in many people's life. And this is a new model that the science conduct with the help of the government, putting companies together and starting centers for new technology all around the country, that at the same time that legitimate the technology also treat patients. A new equipment was developed. I think this is the first equipment that a doctor can see that he treats a cancer, and immediately after the treatment, he knows that he kills everything that should be killed. Normally, this needs to be wait for a long time. So new photomedicine, because now you need molecules that are very efficient in transferring energy of excitation to oxygen to kill the cancer cell. And also, you can know if the tumor is well prepared for receiving the treatment by looking at the fluorescence of those molecules. The protocol is very simple. The doctor sees you can do this application of a medication through in the top of a tumor by topical application or systemic. You do the treatment, and you can see the dead tissue immediately after. And this is being a wonderful technique for lesions that will grow. Those are all skin cancer that's being treated in many places, and in a 20 minutes treatment, everything is done. This is Pakistan. And we have many centers, I'm sorry, it's in Portuguese, many centers established in Brazil, now in Latin America, all those countries, they have centers already doing this technology, which is mainly based in everything we learn in atomic physics and this evolution concept of atom. Those are pictures of those centers. And now we are, together with Johns Hopkins in the United States, we are targeting cervical cancer. Cervical cancer is after breast cancer, is the most important cancer for a woman. And this technique is wonderful. You're just going to put a cream and do the treatment. And cervical cancer up to a level can be well treated with this technique. New devices is being developed, treatments are underway, and I know that in cancer we cannot speak about 100% elimination, but for cervical cancer, in 3 groups of 60 women, we have eliminated 100% of the tumors. But here comes another thing, those reactions. which we call photodynamic reactions because it involves the transference of energy to oxygen, can be applied for many things, including microbiological control. Well, those are applications that has been done in non-cancer treatment, but I want to speak about microbiological control because this is another challenge. And those are a few of the things that's being treated using this technique. Of course, we have to make sure that we can put molecules that are able to transfer energy to oxygen in different places, but those are in situ treatments. We don't need to go to drugs that are systemic. And why is that important? Well, and how that works, first of all, we make the microorganism to absorb some molecules, and by light, we produce the oxidation. And this has been going on, you know, this is the first demonstration of treatment of HPV. HPV is a papillomavirus, and there are many. Today there is even a vaccine, but we have 25% of Brazilian women sexual active contaminated with HPV, and we gotta do something to prevent them to transfer the disease. And this is a well applied technique. Overall mouth decontamination is being done pre-surgery or with surgery. There is a very important application. I'm not going to speak about this leishmaniasis, but in doing mouth decontamination, we develop a technique for preventing the abuse of antibiotics in infants by spraying some substance on the throat and 10 minutes of illumination. We are decreasing the infection of the throat of young kids down to 5% of the original infection. And that's enough for the body to react in that. Okay, and onicomicosis. I didn't know what was onicomicosis until somebody started to apply. This is a fungus that many people has in the nails, and people take fungicide. And I don't know if you know, but the number of liver cirrhosis by fungicides is increasing 300% in 20 years. And women are the main target, and we never faced so many women with cirrhosis. And I thought the woman was drinking too much, because if you drink too much, you get cirrhosis. But no, it's because they are using a lot of fungicide. And you have to find different ways of going. And, you know, everything we understand about atoms and molecules are helping that. And people now, just combining light interacting with atoms can make a big difference in those treatments. And now people put another challenge to us. We know that malaria and dengue are important diseases. And people know that we have to eliminate the vector. And how are we going to do that? We cannot just throw pesticide, you know, the lakes of Africa. But we are able to identify some molecules that those larvae, either of malaria or dengue, can absorb. And the sunlight can oxidize them and kill them very efficiently. So the experiments on a controlled way are killing basically 100% of larvae of malaria and dengue. And Sanofi, which is a big company, gave to us a prize of promising technology in health because of this work. So, and what's interesting, you may think you're going to throw some molecules in the lakes where the larvae are, and then the larvae absorb and the sun will oxidize, and how will be the other organism? And then these molecules just disappear, they oxidize also. So to conclude, you see that the conception of atoms and molecules and their interaction with light is making a big difference in everybody. And I think this cartoon that is 20 years old, that the future is safe, it's our friend's Mr. Atom there. And I think this is true. If we can interact better, understand better the atoms, we can do much better for life. Thank you very much.